Hi guys, today what we're going to do is look at more stoichiometry problems, but instead of just looking at this from a gram to gram perspective, we're going to throw in some other twists with this guy and deal with molarity. So what we specifically looked at in the last video was pretty much just this relationship right here between grams and moles. But as we introduced, there are all sorts of other things that you could do. And specifically what we are going to look at is this one here between the moles and a solution. So remember that a solution is made of two parts. The solute, which is the stuff that you dissolve, the solvent, which is usually water, but it doesn't have to be water, and then the solution, which is the two of them together, the one dissolved in the other there. So molarity is the combination of the solute and the solvent together. As evidenced by this string of different pictures here with these different letters in front of it, you can see that these solutions are of different molarities. This guy here is of low molarity. This guy here is of high molarity. This guy here is concentrated. And then this guy here is dilute that's there. So what we've got going on here is we've got different possible concentrations. And the equation that is used for this is the equation that molarity is equal to the moles per liter. So if you know molarity, moles, and liters, you can figure out what that relationship is. Or if you prefer, molarity times liters is equal to moles, or if you prefer, liters is equal to the moles per the molarity, however it is that you want to go about doing these problems. So all three of these equations are the same equation, and it's this guy here, molarity is equal to moles per liters. You also need to remember, of course, that there are 1,000 milliliters in a liter. So if you're going to go from milliliters to liters, you got to divide. If you're going to go to liters to milliliters, you multiply. That's just basic metrics. So in this particular problem, it says how many milliliters of 0.5 molar nitric acid is needed to react with 43 grams of the barium hydroxide. So you're going to do the exact same things that you did before. It's just that in this one, I've got 43 grams of this, and I want to know how many milliliters are going to be here. But the only thing that they told me was that it's 0.5 molarity. Well, how am I going to get to milliliters? Well, let's walk through it step by step. The first step is to make sure that you turn this into moles. So barium hydroxide weighs 171.3 grams per mole. So 171.3 divided by, or 43 divided by the 171.3 gets you about 251 moles here. Now we're going to go over here by our ratio. So remember, we've got a 2-to-1 ratio there. So we're going to multiply this by 2 and divide it by 1 because, again, you got to take those numbers there into your account. And so then you're looking at about 0.502 moles here. All right, so I want to get from moles to molarity. Well, in order to do that, remember, I need to know, or moles to liters, I should say. I need to know what the molarity is. Well, remember, they told you what the molarity is. It was 0.5 molarity. So now what you're going to do is you're going to use your equation. Molarity is equal to moles per liter. And so my molarity, I told you over here, was 0.5. So that's 0.5. And I also told you that it was 0.502 moles. And so then you want to know what the liters are. So you're going to divide the 0.502 by the 0.5, and you're going to get 1. So you're going to get 1 liter, or you're going to get 1,000 milliliters. So in this one, it worked out really convenient. This is 1,000 milliliters for that to occur. Number 2 here says how many grams of lead chloride can be precipitated out from using excess lead nitrate with 55.2 milliliters of 0.75 molar NaCl. Holy cats, right? Okay, so for these guys, I want to know grams of this. And what did I tell you? I told you that you used 55.2 milliliters, and it was 0.75 molarity there. So using the milliliters and the molarity, first thing I have to do is turn that to liters. So that's 0.0552 in liters. And then again, we're going to use the equation that molarity is equal to the moles per liter, except this time I'm looking at the moles. Because again, in all of these problems, you're going to start with some real world problem, and then you're going to come down here to get to mole world. So if I have 0.0552 liters at 0.75 moles per liter, then that is going to get me 0.0414 moles here. But I don't want this stuff, I want this stuff, so I got to work my way across town. So that's where the mole ratio comes into play. I'm going from a 2 to a 1, so that's going to get cut in half, because again, you always multiply by where you're going, divide by where you came from. I'm going over here and I'm dividing by from there, because that's where I'm coming from. And so that's going to get me 0.0207 moles here. And now I want grams, so again, like we learned in the last segment, if I want to go from moles to grams, and then now I got to use the molar mass formula, just like I did in the last segment that we learned about. So I add up lead and 2 chlorines, and I get 278.2 grams per mole. And when I'm all said and done, this should be about 5.76 grams if I have done my math on this properly. Number 3 says, what is the molarity of the solution? So now I want the molarity of the solution. So what did they tell me? Well, they told me that I had 37.2 milliliters of this stuff. So I can go ahead and throw that in. That's 37.2. Again, that's a real world measurable kind of a thing. But it also told me that I had 0.48 grams of this stuff. And I want to know what the molarity is. Well, remember that the molarity is equal to the moles per the liter. Well, I have one of those things right now. I have the liters because I have the milliliters. So I'm going to cross this off and I'm going to replace it with 0.0372 liters because you got to divide by 1,000. So right off the bat, I'm halfway there and I haven't even really done anything. So that's going to be 0.0372 liters, but what I really need, look at that, check it out. What I really need is the moles of this stuff. Well, I don't have the moles of that stuff, but I can get it because I have the moles of this stuff. So this guy here, if I add up his molar mass, that's going to be 204.1 grams per mole. And that's going to get me about 0.00235 moles when I do that math. And now I got to go across town, and when I go across town, this is an easy one. It's a 1-to-1 ratio. So this is a 1-to-1 ratio, so that means it's going to be 0.00235 moles here. And so now I know the moles, and I know the liters, so this is going to be 0.00235 moles divided by the 0.0372 liters. When it's all said and done, your molarity is going to end up being 0.00235 moles divided by 0.0372 liters, or I'm going to end up with about a 0.0632 molarity. Number 4 says, what was the molarity if 3.2 grams of silver phosphate go together or collected from the precipitate after 28 milliliters of silver nitrate was reacted with excess of the sodium phosphate there. So what do I have? I've got 3.2 grams. And again, I want to know what the molarity is over here for this guy. I want to know what the molarity is, which means I'm going to need to know what the moles are, and I'm going to need to know what the liters are. Well, they already told me the liters. They told me it was 28 milliliters. So if it's 28 milliliters, then I know right off the bat it's 0.028 liters that I can plug into my equation here because I know how many milliliters are in a liter. The only thing I need is the moles. Well, I don't have the moles, but I can get the moles because I have grams here. This stuff here weighs 418.7 grams per mole. So when I divide that out, I get about 0.00764 moles of the silver phosphate. Well, if that's the case, and knowing my balanced equation, I can come back over here to this stuff by a 3-to-1 ratio, because it's a 3-to-1 ratio there. And I would end up with about 0.0229 moles of this. And now that I know the moles, then I have this 0.0229 moles that were being divided by 0.028 liters. My molarity ends up being about 0.819 molarity when it's all said and done.